Okay, we're starting with chapter 2, the motion in one dimension. This is a fundamental and a critical chapter for you to understand. Uh, we will be using these equations of motion throughout our study of physics. In the next chapter, we'll study vectors, and after vectors, we're going to do motion in 2 dimensions. And we're going to see these equations of motion over and over and over throughout our study of physics. Even in the second semester when we study electrons and protons and talk about their velocities in a magnetic field. So it is critical that you understand this motion in one dimension. If you have problems with part of what you're learning, you need to ask me for help, and I'm willing to give it. So let's get started. Okay. A particle's position, x, is the location of the particle with respect to a chosen reference point, usually the origin of some given coordinate system. The particle's motion is completely known if the particle's position in space is known at all times. Figure A shows a car moving back and forth along the x-axis. The portion on the left-hand side is a pictorial representation of the car moving. At point A, the car is 30 meters to the right of the reference point, x equals 0. Using the particle model, we identified a point on the car, for example, the front door handle, as representing the entire car. We can reference it as just a sphere for analysis purposes. We use intervals of 10 seconds to record the car's position. From the table, we can see that the car moves to the right, the positive direction, from A to B during the first 10 seconds of motion. After B, the position values decrease, which indicates that the car is backing up from B through F. At D, 30 seconds after we start measuring, the car is back at the origin. The car continues moving left more than 15 meters to the left of x equals 0 when we stop recording. Below the table is a graphical representation of the position versus time graph. Now, you have to pay attention. The motion of the car is this way, but the horizontal axis of the graph is time, not position. The vertical axis is position. So you have to pay attention to that. Let's go to the next slide, and we've got alternate representations of the same information. We have the pictorial representation. That's the image of the car. We have a tabular representation. That's the table of data that we were given. And we have a graphical representation. Different representations can help in understanding physics, the physics of the situation. Usually, the ultimate goal is a mathematical representation. We're actually going to solve the problem. Displacement. Displacement delta x of a particle is the change in position in a given time interval. As a particle moves from the initial position x sub I to a final position x sub f, the displacement is given by delta x is x final minus x initial, xf minus xi. Delta denotes a change in quantity. That's a Greek letter D, delta, same as D, and it stands for difference. From the equation, we can see that delta x is greater than 0. That is positive. If x of f is, if x final is greater than x initial, and delta x is negative, less than 0, if x final is less than x initial. Okay, let's further discussions on distance and displacement. Displacement and distance are different. The distance is the length of path followed by a particle. As an example, the basketball players in the figure, if a player runs from his own team's basket down the court to the other team's basket, then returns to his own basket, the displacement is equal to 0. Because x final minus x initial, because x final equals x initial, x final minus x initial equals 0. So delta x equals 0. During this time interval, the player moved through a distance twice the length of the basketball court. Distance is always positive. The displacement can be positive or negative. Displacement is a vector quantity. That is, it has a magnitude and direction. Other vectors are position, velocity, and acceleration. Okay. A vector quantity has both magnitude and direction. Example, how far did the position of the car change, the magnitude, and in what direction, forward or backward? So it has a magnitude and direction. A scalar quantity has numerical value only and no direction. Example, how far did the car move as measured by the odometer? Your odometer only goes forward, hopefully, unless somebody's cheating you. Your odometer only goes forward and never backward. So the scalar quantity, the distance is always positive. We use positive and negative signs to indicate vector direction. Typically, we assign right as positive for the horizontal motion. Right is the positive direction, and we assign up as positive for vertical motion. Those are typical. So let's look at this graph again. From the data in the table, there are only 6 data points in the graph. So the motion of the particle is not completely known because we don't know its position at all times. A smooth curve drawn through the 6 points in the graph is assumed. It is only a possibility of the actual motion of the car. I mean, if any of you are used to Excel, you know that you can join lines of a X versus Y graph with curved lines. Well, that's Excel is trying to figure out what it's doing. It's not necessarily accurate, but it looks pretty. We only have information about 6 instants of time, and we have no idea what happened between the data points. We can only guess as to what happened, and we guess that it's a smooth curve. If you get into digital electronics, you get into sampling. You can have a motion that's like this, but if you sample it just right, you'll get you can get a smooth curve. It has to do with resolution. It's the same. The sampling is the same reason. If you ever look at the old videos of old westerns, when a wagon wheel slows down, it appears to stop, and then it even rotates backward. That has to do with the sampling rate of the movie camera. It's an optical illusion. Okay, time for a little quick quiz. Which of the following choices best describes what can be determined exactly from the table and figure for the entire 50-second interval? The distance the car moved, the displacement of the car, both A and B, or neither A and B? Give you some time to think. And the only thing that we can really determine is the displacement of the car. All we can do is tell how far it's moved from over the entire period. Okay. I have to go through slide 9, and this is the last slide. Okay. It's easier to see changes in a position graph than from verbal description or a table of numbers. From the graph, the car covers more ground during the middle 50 seconds interval than at the end. Between positions C and D, the car changes position by almost 40 meters. During the last 10 seconds between positions E and F, down at the bottom there, it changes position by less than half of that much. You can compare different motions by dividing the displacement delta x by the value of a corresponding time interval. And the result is you get an average velocity of the period under question. Average velocity, v sub x average of a particle is the particle's displacement delta x divided by the time interval delta t during which displacement occurs. Vx average is defined as delta x over delta t, the displacement over the time. The subscript x indicates motion along the x-axis. The average velocity, the dimensions of which are length divided by time. Meters per second in SI units, but it could be miles per hour, centimeters per second. But we usually use meters per second. Okay, the average velocity of a particle moving in one dimension can be either positive or negative. It depends on the sign of the displacement. The time interval delta t is always positive. If the coordinate of the particle increases in time, that is, if x sub f, the x final is greater than x initial, then delta x is positive. Vx average equals delta x over delta t is positive. It corresponds to a particle moving in the positive x direction toward larger values of x. If the coordinate decreases in time, that is, if x final is greater than x initial, then delta x is negative. Vx average is negative means that it corresponds to the particle moving in the negative x direction. And that's I think that's the end of the. Oh, no. Okay, we're going through 16. I apologize. I was looking at chapter 1 notes. Okay, the geometric interpretation of average velocity. Let me put it here. The geometric interpretation of average velocity is as such. You draw a straight line between any 2 points on the position versus time graph. The line forms the hypotenuse of a right triangle of height delta x and base delta t. The slope of the line is delta x over delta t, and that's your average velocity. As an example, the line between positions A and B in the figure has a slope of the average velocity of the car between these 2 times. And it's approximately 52 meters minus 30 meters over a 10-second interval. That's 2.2 meters per second. Okay? It's 22 divided by 10. So that's 2.2 meters per second. Okay. Now, the average speed of a particle, whoa, sorry, I hit a cat accidentally. In everyday usage, speed and velocity are interchangeable. Not so in physics. There's a clear distinction. Consider a marathon runner who runs a distance d of more than 40 kilometers and ends up at the starting point. The total displacement is 0. His average velocity is 0. How fast was she running? Well, the average speed of a particle, a scalar quantity, is the total distance d traveled divided by the total time interval required to travel the distance. So V average is equal to the distance divided by delta t. In SI unit, the average speed is the same as the unit of average velocity, meters per second. Average speed has no direction. It's always expressed as a positive number. Average velocity is the displacement divided by the time interval, and average speed is the distance divided by the time interval. So you need to understand that difference. The knowledge of average velocity or average speed of a particle does not provide any information about the details of the trip. For an example, if it takes you 45 seconds to travel 100 meters down a long straight hallway at an airport, let's say at the 100 mark, you return back 25 meters along the same hallway, taking 10 seconds to make the return trip. The magnitude of the average velocity is, because you went back 25 meters, it's 75 meters divided by 55 seconds. That's 1.36 meters per second. Your average speed, remember, it's not the displacement, it's the distance. So it's 125 meters divided by 55 seconds. It was 2.27 meters per second. You may have traveled at various speeds during the walk, and of course, you changed direction. Neither the average velocity nor average speed provides information about these details. Okay, let's do a little quick quiz. Under which of the following conditions is the magnitude of the average velocity of a particle moving in one dimension smaller than the average speed over the time interval? A, the particle moves in the plus direction without reversing, or the particle moves in the minus x direction without reversing. A particle moves in the x direction and then reverses the direction of its motion. There are no conditions for which this is true. And if we look, it's C. A particle moves in the x direction and then reverses the direction of the motion. Okay, here's some examples. Find the displacement at average velocity and average speed of the car in the figure between positions A and F. That's from the beginning, the left hand of the graph to the right hand of the graph. Look at the figure to form a mental image of the car and its motion. We model the car as a particle. From the position versus time graph, notice that x sub a equals 30 meters and at t sub a equals 0 seconds. And that x final is minus 53 meters at t final equals 50 seconds. Use this equation, delta x equals x final. That's not x final, that's x at position F minus x at position A to find the displacement of the car. Minus 53 meters minus 30 meters, that's a total of minus 83 meters. This result means that the car ends up 83 meters in the negative direction from where it started. This number has the correct units and is of the same order of magnitude as the supplied data. A quick look at the figure indicates that it is correct. Okay. Now, what is the average velocity? And you use this equation, the x sub f minus x sub a divided by tf minus ta. You get 53 minus 30, which we've already determined is 83 meters, divided by 50 seconds, and you get it's a minus 1.7 meters per second. Okay, and let's calculating the average speed. We cannot unambiguously find the average speed of the car from the data in the table because we do not have information about the positions of the car between the data points. If we adopt the assumption that the details of the car's position are described by the graph, the distance traveled is 22 meters from A to B, plus 105 meters from B to F, for a total of 127 meters. Use this equation to find the car's average speed. 127 meters divided by 50 seconds is 2.5 meters per second. Notice that the average speed is positive, as it must be. Suppose the red-brown curve in the figure were different, so that between 0 seconds and 10 seconds, it went from A to 100 from A up to 100 meters and then came back down to B. The average speed of the car would change because the distance is different, but the average velocity would not change. This ends our discussion of section 2.1. Next, we will discuss section 2.2, instantaneous velocity and speed.